Welcome to the tutorial. Setup of the PW function block pulse width modulation in EZ4. This video tutorial shows how to configure the PW function block. The following technical requirements must be met: an EZ4 basic device, an EZsoft programming software version 7.x or 8.x. A license is required for the EZsoft programming software. You can download software, firmware and updates at www.eaton.com/software. In pulse width modulation, a square wave signal with a constant period duration frequency is generated. The ratio between pulse and pause duration is variable. The ratio between pulse and pause duration can be changed via the control variable. The frequency does not change. This ratio is called duty cycle and is given as a decimal number or as a percentage. If a duty cycle of 0.5 or 50% is set, the pulse and pause duration are the same. The practical thing about this is that the duty cycle is easy to determine the output power of a controlled consumer. If a consumer with a nominal power of 100 watt is controlled by means of pulse width modulation and sets the duty cycle to 50%, the output power corresponds to 50 watt. The selected period duration is not important and is chosen depending on the application. If the pulse width modulation is displayed on an oscilloscope, pulse and pause time can be observed or measured. An analog signal from a potentiometer was used as the control variable. Between the vertical cursors A and B, you can see the set period duration of about 5 milliseconds. If the variable SV is varied with the potentiometer, it can be seen that the pulse width changes, while the period duration remains constant. What is pulse width modulation used for? If consumers are controlled using PWM, the power can be changed. For example, heating resistors, lamps, or DC motors can be variably controlled. Furthermore, operating equipment such as servo motors, proportional valves, motor sliders, blind flaps, frequency converters, and much more are available, which can process pulse width signals in order to be controlled by a controller. On the left, you can see the principal diagram for controlling the rotation angle of a servo. On the right, the control variable of a PI controller for temperature control. The EZ-E4 control relay has two digital outputs that support pulse width modulation. Q1 and Q2 are the base unit. Each of these outputs is assigned a PW function module, PW01 and PW02. The assignment of PW01 to Q1 and PW02 to Q2 cannot be changed and therefore does not have to be parameterized in the program. This means that if you use the PW01 module in your program, the Q1 output is automatically used for the pulse output. The output must not be used again in the program to write, because it is already controlled by the PW function. A tip: select a function block in EZsoft with a single click and then press the F1 key to open the corresponding section for the block in help. With the input EN, enable, the module can be activated or deactivated by the program. SV is the input for the control variable, for example the duty cycle. Here, values from 0 to 4095 can be passed to the function, which corresponds to a duty cycle of 0 to 100%. The AD converter of the EZ-E4 analog inputs, as well as the output of the PID controllers of the EZ, are value compatible, so that their outputs can be linked directly to the PW devices. You pass the desired period duration in milliseconds to the input PD. At input ME, the minimum switch on and switch off times are passed in increments. This means that if the control variable SV is so small that this set minimum duty cycle is not reached, no pulses are output. The same applies to the minimum switch-off time. If the control variable SV is so close to the maximum that the minimum switch-off time is not reached, the PWM output remains constantly switched on. An example: if the period duration PD is set to 5 milliseconds, which is the shortest possible period duration, divide the 5 milliseconds by the maximum value of SV, which is equal to 4095 increments. This results in a factor of 0.00122 milliseconds per increment. If you were to pass 20 increments to SV as a control variable, the set pulse time would be 0.0244 milliseconds. Due to the hardware, the shortest switch on and switch off times are 0.1 milliseconds. In this case, the PWM output remains switched off because the minimum duty cycle is not achieved with this SV. To understand the interaction of ME, minimum on, minimum switch off time, and the device output E1, here is a short excursion to the output E1. Output E1 indicates with a true whether, firstly, the device has been parameterized incorrectly, PD is lower 5 milliseconds, wrong PD to ME ratio. Or secondly, the PWM device works at the lower or upper limit of its adjustment range. This second reason for reporting to E1 should be regarded as a status message because it can be used to draw important conclusions about the control by a controller module during the running program. Here are some calculations for point 2. Since the minimum power on and minimum power off time can be as low as 0.1 milliseconds due to hardware, the minimum power on and minimum power off time in increments is 0.1 milliseconds divided by 0.0012 milliseconds per increment, which corresponds to approximately 83 increments. Only at SV equal to 86 is the duty cycle 120 microseconds, correspond to 0.12 milliseconds, then E1 becomes false and the pulse is output. The same applies to the minimum switch-off time from the upper end of the setting range. To sum up, for PD equal to 5 milliseconds, if a value lower 86 or greater 4016 is passed to the input SV, the PWM output is permanently switched off or on permanently. For checking, this is indicated at the E1 device output with a true. So you can see at output E1 whether the control of the PW is working at the upper or lower limit. The above only applies to the period duration of 5 milliseconds. If you use a longer period duration in your program, there are different, smaller values for the minimum switch on and minimum switch off time. In this diagram for the minimum duty cycle, you can see which pairs of values lead to the setting of the output E1 and thus switch off Q1, namely all pairs of values below the chart line. The same applies to the minimum switch off time at the upper end of the SV value. The question is, what do you do with the ME input? An example, as illustrate, if you connect an electromagnetic switchgear, for example contactor, to the transistor output of the EZE4, you have to consider the inertia of the switchgear. The same considerations must be made for EZ4 with relay outputs, T on T off equal to 10/5 milliseconds. For the example below, let's assume a PD of 3000 milliseconds. With the EZE4, you have implemented the temperature control of a drying oven. To control the heating resistor, use a DIL-M12 contactor, 24 volt DC. The closing time is lower 31 milliseconds, the opening time lower 12 milliseconds, the maximum switching cycles per hour are 9,000, and the mechanical service life is 10 million switching cycles. If the above-mentioned contactor is used to control a heating element by PWM, the switching times, switching cycles per hour, and mechanical service life should be included in the considerations. The following is an example calculation of the service life. PD equal to 1000 milliseconds, 3600 cycles per hour means 115 days mechanical, 24/7 hours operation. PD equal to 3000 milliseconds, 1200 cycles per hour means 347 days mechanical, 24/7 hours operation. For the example below, let's assume a PD of 3000 milliseconds. With a PD of 3000 milliseconds and a maximum control variable of 4095 increments, this results in a resolution of 3000 milliseconds divided by 4095 increments is equal to 0.73 milliseconds per increment. Means the PI temperature controller calculates a required control variable SV of 1 increment. The contactor would be controlled for approximately 0.7 milliseconds. However, it takes up to 31 milliseconds to fully tighten up, and only then does the current begin to flow through the heating resistor. In order to obtain a heating effect, the contactor must be controlled for longer, for example at least 100 milliseconds. This can be set with the parameter ME. minimum on, minimum switch off time. If set for me equal to 100 milliseconds, all control variable values at the input SV up to 100 milliseconds divided by 0.73 milliseconds per increment equal to 136 increments ignored by the PW function module, and no pulses are output at output Q, E1 equal true. Only from a control variable of 137 increments pulses with a duration of 100 milliseconds are output. The minimum current flow time is then pulse duration, 100 milliseconds, minus contact to pickup time, 31 milliseconds, which is around 69 milliseconds. The ME parameter also refers to the minimum switch-off time. From this follows, SV equal 4095 increments minus ME equal 137 increments is equal to 3958 increments. If an SV lower 3958 is transferred to the function, the output Q of the PW is switched on permanently. Similarly, E1 equal true indicates that the value is in the limit range. In summary, one can say, select a period duration that suits the actuator or application and set a minimum duty cycle that also has an effect on the process without overusing the actuator. Solid-state relays, in conjunction with EZ 4-transistor variants, are an alternative to electromechanical switchgear. Semiconductors, thyristors, are used to switch the load currents, which are not subject to mechanical wear. Of course, solid-state relays switch silently and faster than contactors and relays. With the solid-state relay shown, the current flow begins after only 10 milliseconds. In this case, the minimum duty cycle can be reduced and the period duration shortened. A general statement about good settings for pulse width modulation is not feasible, as it always depends on the switching devices used and the inertia of the variable to be controlled, meaning the correct settings depend on the application. Thank you for your attention.